I want to tell you about something that happened today with 3I Atlas. And honestly, it's the kind of thing that makes you sit back and realize we're watching something genuinely unusual unfold in real time. So, NASA was going through the daily data for this interstellar comet, right? The same routine they do every single day. Telescopes all over the world send in their observations, spacecraft add their measurements, and everything gets fed into these incredibly precise orbit calculations. It's the kind of work that usually produces numbers so consistent, so predictable, that you could set your watch by them. Except today, those numbers didn't line up the way they were supposed to. And I don't mean in some tiny, negligible way that you could brush off as instrumental noise or atmospheric distortion. I mean in a way that made the tracking team stop, recheck everything, and then realize that 3I Atlas had actually changed its trajectory. Again, before we continue, if this has your attention, you can subscribe, turn on notifications, and hit like anytime. And for the best viewing, switch to full screen and enjoy what's coming next. Now, before you think I'm being dramatic, let me explain what I mean by that. Obviously, comets move. That's what they do. They orbit. They follow predictable paths based on gravity and physics and all the fundamental laws that govern how objects travel through space. We're really good at calculating those paths. Give us enough observations, and we can tell you where a comet will be months or even years from now, down to incredibly small margins of error. But here's the thing about 3I Atlas. It's not just following gravity anymore. It hasn't been for a while now. It's actively pushing itself in ways that keep surprising us. And today was another one of those moments where the data came in, and everyone had to acknowledge that this object is doing something our models didn't fully account for. Let me walk you through exactly what happened, because the details matter here. Every observatory that tracks 3I Atlas sends in position data. These are incredibly precise measurements, just dots on the sky with exact timestamps attached to them. You take all those dots, plug them into an orbit solver, let the software calculate where gravity should be pulling the comet, add in a small correction for outgassing, the gas and dust jets that comets naturally produce as they warm up near the sun. And if your model is accurate, the differences between where you predicted the comet would be and where it actually is should be microscopic. We're talking fractions of an arcsecond. Tiny discrepancies that are mostly just measurement uncertainty. Yesterday, those differences were well within normal limits. Everything looked good. The comet was right where it was supposed to be, give or take the usual observational scatter. Today, when the new measurements came in and got run through the tracking software, something changed. The residuals, those little misses between prediction and observation, they weren't scattered randomly anymore. They were biased, systematically offset in one particular direction. The comet was consistently showing up a little bit to one side of where the model said it should be. Now, the first thing you do when you see something like that is assume it's an error on your end. Maybe the reference stars used for positioning are off. Maybe there was a timing issue with one of the observatories. Maybe something in the calibration wasn't quite right. These things happen. Astronomical observations are incredibly precise, but they're not infallible. So the teams went through everything. They pulled data from multiple sites, different telescopes, different cameras, different parts of the world, northern hemisphere, southern hemisphere, the works. If this was just one telescope having a bad night, the others would show the comet in the right place. But they didn't. Every single observation showed the same offset, same direction, same magnitude. The comet was consistently displaced from its predicted position. And then, just to make absolutely sure this wasn't some systematic error affecting all the ground-based telescopes, they checked the spacecraft data. There's a solar observatory that's been quietly tracking 3I Atlas and its coronagraph images, and it had just sent in an updated position measurement. This is an entirely different type of observation, different instrument, different method, completely independent of the ground stations, and it showed the exact same thing. The comet was off the predicted track in the same direction. At that point, there was no getting around it. This wasn't an observational error. This wasn't bad data. The comet had genuinely moved, not just forward along its orbit, which of course it's constantly doing, but laterally across its predicted path. It had shifted to one side. To get the orbital model to fit the new observations, the teams had to go back and adjust what are called the non-gravitational parameters. These are the parts of the equation that account for all the little pushes and shoves that come from the comet's own activity. Every time a jet of gas bursts out from the surface, it acts like a tiny rocket thruster, giving the comet a little push. Usually, most of that push is in the direction the comet is already moving, either speeding it up slightly or slowing it down slightly. That's the normal behavior we see with most comets. But yesterday's orbital solution was based on that assumption, that most of the non-gravitational force was acting along the direction of motion. Today's data says that's not enough anymore. To make the model work, they had to increase the sideways component of that force significantly. What that means in plain terms is that 3I Atlas is now being pushed more sideways than it was before. The pattern of its outgassing, the jets and vents that are spewing material into space, they've changed in a way that's altering the comet's trajectory in real time. And here's where it gets really interesting. While the orbital specialists were working on that problem, the imaging teams were doing their own analysis. They've been taking deep exposure photographs of the comet, long integration times to capture as much detail as possible in the coma and tail. They stack multiple images together to bring out faint structures, and then they compare those stacked images from day to day to see how things are evolving. When they compared yesterday's image to today's, they saw something that perfectly matched what the orbital data was telling them. The tail hasn't dramatically swung around or anything that dramatic. On the large scale, it still points generally away from the sun, which is exactly what you'd expect. Solar radiation and the solar wind push comet tails away from the sun. That's basic comet physics. But when you zoom in close to the nucleus, into the inner coma, the region just a few tens of thousands of kilometers from the comet's core, that's where you see the change. The whole structure is skewed. The brightest part of the inner coma, the densest concentration of gas and dust, is offset in the same direction as that orbital drift. The main jet, instead of pointing directly away from the sun like you'd normally expect, is canted off at an angle. Think of it this way. Yesterday, if you looked at the comet's activity, it was like looking at the exhaust plume coming off the back of a car driving down a straight road. Pretty much what you'd expect, a plume pointing backward along the direction of motion. Today, it looks like that exhaust is being blown sideways, or like someone physically turned the tailpipe. Either way, the net result is the same. The push the comet is experiencing from its own outgassing is no longer aligned with its direction of travel. It's pushing the comet off to one side. And there's more. The rotation data has picked up something odd as well. Astronomers measure how a comet's brightness changes as it spins. Because comets aren't perfect spheres, they have irregular shapes, they have brighter and darker patches on their surfaces, and as they rotate, those variations cause the overall brightness to fluctuate in a predictable pattern. We call this the light curve. The rotation period of 3I Atlas hasn't jumped dramatically like it did on some previous days when we saw those sudden changes, but the shape of the light curve has definitely shifted. Where before you'd see one strong brightness peak per rotation and then a softer, less pronounced secondary peak. Now that secondary peak is becoming sharper, more defined, and it's arriving earlier in the rotation cycle. That's a telltale sign. It means a vent that was previously weak, or maybe even dormant, has become more active. It's now contributing more strongly to the overall brightness and to the total outgassing. A different part of the comet's surface has woken up. So when you put all of this together, you get a really clear picture. The orbital calculations say the comet is being pushed more sideways than it was. The images show the inner coma leaning in that same sideways direction. The light curve indicates that a different combination of vents has become active. Everything is consistent. Everything points to the same conclusion. 3I Atlas has reconfigured itself. Its engine, if you want to think of it that way, has changed. And that change is now actively altering the path the comet takes through our solar system. So the obvious question is, why? What happened inside this object to cause this change? There are a few possibilities, and honestly, all of them are pretty fascinating. One idea is that the heat from the sun, from the comet's close approach a while back, has finally penetrated deep enough to reach a reservoir of volatile ices that was buried beneath the surface. Not just any reservoir, but one that's offset from the center, not symmetrically placed, maybe sitting under a particularly thick or tough patch of crust. When that pocket of ice finally got hot enough, it didn't just gently leak out, it punched through, blew off the overlying crust, and opened up a new major vent. Now you've got this powerful jet firing from a part of the nucleus that wasn't doing much before. And because it's offset, because it's not firing from the center or in a balanced way, it's adding a significant sideways component to all the existing forces. Another possibility has to do with the comet's rotation.